Hello everyone, this is section 1.6, relative motion. Relative velocity is a concept describing a motion seen by different point of view. For example, if you're traveling in an airplane above clouds, all smooth with a constant velocity, and you watch from window, clouds look they are moving, not airplane. If you see the airplane wing, most likely it will give you an impression that airplane is just floating, not flying, not moving. However, if you see the same airplane from ground point of view, you are on the ground and then watch the airplane, there is no doubt that airplane is moving. In a similar way, you might have experience when you are inside of the train and train is moving smooth at a constant velocity. You may actually look outside and see the platform, the walls, ads outside, and you are wondering, are those ads moving or you with the train are moving? So, however, if you are outside waiting in that platform, waiting for a train, there's no doubt then when you see a train entering the platform, it is for sure the train is moving. So the same motion seen by different point of view look and feel differently. That is relative velocity, relative motion. So the passenger in plane or in a train are in one frame of reference or have one point of view. An observer on the ground or on a train platform have another frame of reference. However, what is a frame of reference? It's a coordinate system relative to which the motion is described or observed. Same motion can be seen and described differently from different point of view, as you saw on those examples, from different frame of reference. So velocity of an object relative to a specific frame of reference is called relative velocity. Now, if we have three objects and we analyze the object velocity, so if the velocity of the object A relative to object B is VAB, and velocity of the object B relative to C is VBC, then the velocity of A relative to C is VAC and is a vector addition of VAB plus VBC. If you take a look there, it's about VA and VC is about first and last vector. However, those two velocities are connected internally. So velocity of object A relative to B and object B relative to C has to be pretty much internal link. That's how you can write it, that's how you can express it. And then velocity of the object A, which is the first one, relative to the object C, which is the last one. What about if you have more than three? What about if you have four objects? That is the same thing. First and last object. So we're talking about velocity, the first object relative to the last one is equal to velocity of the object 1 relative to object 2 plus velocity of object 2 relative to 3 plus velocity object 3 relative to 4 is equal to object 1 relative to 4, to fourth object. So you can see that it is easy to track. So it's about first object and it's about last object. And everything in between, they are connected together, but nothing to do with velocity of A relative to object d. Let's do an example so you see if you can understand. A sailor walking on a boat, and a boat is moving on a river. River water is moving relative to land. Find the velocity of the sailor relative to land. You can write the relationship yourself. Pause the video and see how much you have learned. You can look at the 4-object example and actually try to write velocity of a sailor relative to land. So sailor has to be the first one and land is the last one. And in between is a sailor relative to boat, boat relative to water, and water relative to land. So it is pretty much similar to this one, and I hope you can do it. Yes, you can. Pause the video and try it. If you wrote like this, then you understood the relationship between relative velocities. So velocity of a sailor relative to land is equal to a velocity of a sailor relative to boat plus velocity of the boat relative to water plus velocity of the water relative to land. So you see everything in between are connected and everything outside is the one that you are looking for. Here is the practice problem with a relative velocity. This is easy one, motion in one dimension, motion in a straight line. If the plane is moving relative to air at 450 kilometers per hour north and the air velocity relative to Earth is 40 kilometers per hour north, find the velocity of the plane relative to Earth. So what is given? It's a velocity of plane relative to air, VPA, is equal to 450 kilometers per hour north. Velocity of air relative to Earth, VAE, 40 kilometers per hour north. What is velocity of plane relative to Earth? Now, the formula is velocity of plane relative to Earth is equal to a velocity of plane relative to air plus velocity of air relative to Earth. It's a vector addition. Thing is, it is in one direction, straight line, one direction. That's easy, so you can do that calculation right away. 450 kilometers per hour north and 40 kilometers per hour north. Both of them are the same direction, north. So the answer would be velocity of plane relative to Earth is 490 kilometers per hour north. Relative velocity can be a vector addition of the two vectors that are not at a straight line. They may be two-dimensional vectors. However, we already learned how to deal with two-dimension vectors, how to calculate component of each individual vector, how to add them together. You can add all x's together and all y's together, and then you can add them up and draw them. You can draw a total, which is going to be a relative motion in this case, and then using a Pythagorean theorem and tan -1, you are going to find magnitude and direction of the relative velocity. It is exactly what we did before with total velocity. It is exactly what we did before with a total displacement. So relative velocity, it is a vector addition of the two vectors or two velocities that are related to each other. Sometime we may have two velocities, sometime may have three. We use the same. We add all x component together and we add all y component together to find that total or relative velocity. But we should do some practice. Otherwise, it is very difficult to understand the concept without doing practice. Here is another problem. A motorboat steers straight across the river at a constant velocity of 10 kilometers per hour north. The river is 0.30 kilometers across, and its current is 5 kilometers per hour east. So we have two dimensions. We have north, one velocity, and east, another one. How long will it take to cross the river without water flowing? So that means, for a moment, let's ignore the current for 5 kilometers per hour east. Let's say that the water is not moving. Then it's going to be a constant motion. So what we have there is a velocity of boat relative to water is 10 kilometers per hour. Velocity of water relative to earth is 0. That means it's not moving. Distance across the river is 0.3 kilometers north, and time is required. So we can say time is equal distance over speed or velocity. Since that we know the direction, the distance is, or displacement is toward north, and velocity is toward north. They both have the same direction, they cancel. So it's a straight line. 0.3 kilometers divided by 10 kilometers per hour will give you 0.030 hour. You don't really need to convert it in a second for now, because that's not the point. I want to make a point. Would this be different if to cross the river if there is a flow of 5 kilometers per hour? So how long will it take to cross a river in a normal circumstances when there is flow of 5 kilometers per hour east? Then what we do, take a look. We have two motion now. It's a motion of the boat relative to water and motion of the water relative to earth. So it is a two vectors, and what we use a total vector or vector that represent velocity of boat relative to earth. So what we do is just as we do two-dimensional vectors. What we have there is a velocity of the boat relative to water is 10 kilometers per hour north. Displacement toward north is 0.30 kilometers north, and velocity of water relative to earth is 5 kilometers per hour, or relative to land, whatever you want. So what is time? Now, since that is a constant motion, we can use the same. Time is equal displacement over velocity. Now, total displacement, it is pretty much on a direction of the velocity that adds both velocities. So that total displacement that will reach to this point, it is in a direction of the total velocity, or velocity of boat relative to earth, which is sum of both vectors. Now, if you see that those two triangles, the small one and the big one is with a displacement. That is a y displacement, delta dy displacement. This one is delta dx. I didn't label it. I'll do it later. And this one is delta d total. This triangle is a similar triangle with a triangle of vectors, of velocity vectors. So if you see it is a vector of boat relative to water, vector of the water relative to earth, and this one at the same direction goes to a vector of the boat relative to earth. Now, in order to find the time that travels from this point here, from school to whatever it will land here, because of the flow, you can divide this distance, the hypotenuse of the big triangle, with the hypotenuse of the small triangle, which is velocity. Time is distance over speed, or displacement over velocity, which we already know the direction is exactly theta with north. It's going to be like a north, theta, east. But that's not the point, because we can shortcut it. We can figure out in a different way how to do it. So then we can calculate hypotenuse is adjacent divided by cosine theta. So adjacent for the distance is delta dy. This is adjacent of the angle theta. For a small triangle, what is adjacent? Is a VBW. So VBW is adjacent again of this triangle. So then you express this VBE as adjacent over cosine. But you see the cosine and cosine cancel. You end it up to delta dy. You see that, look at here, delta dy over delta over VBW. So the distance that is straight across divided by velocity that is on that direction, same direction. But we already did this. So that will be delta t is equal 0.3 kilometers north divided by 10 kilometers per hour north. North and north cancel. And then what we left is with 0.03 hours. So the point here is, no matter the direction, the time crossing from one side of the river to another side of the river does not change, because it changes where you land across the river. You don't land at home. If you go straight up, you're going to land at home. But if there's a river is flowing, it's going to take you. So the water is going to take the boat in that direction, and the boat is going to land somewhere here. However, the speed is going to be proportionally with the distance, that is speed that is added, getting bigger, is going to be proportionally with the distance that is getting bigger. So the ratio between delta D total over VBE is still the same. So time is the same no matter if you have current or not. That is like a different what you might expect. You may expect that since that the river is flowing, then you may take time to reach to another side of the river. If you swim, for example, across from this point here to this point, and that's water flowing, taking you in a different direction, then you may reach at a longer period of time, because the water may actually make impossible to go on time. That's not true. That will not affect you time crossing from one side to another. It is going to affect you where you're going to land from what you meant to land. It's going to go in a different direction. That's about it. Now, next step would be determine the boat velocity relative to observer on a riverbank. So relative to Earth. If you see the diagram above, or even that below, because it's pretty much the same thing, is that this diagram, velocity of the boat relative to Earth, it is a hypotenuse of the triangle that is made of velocity of boat relative to water plus velocity of water relative to Earth. So as always, you can use Pythagorean theorem. So it's a vector addition of the two vectors in 2 dimensions. Then you can use a Pythagorean theorem to find the magnitude of that hypotenuse or velocity of the boat relative to Earth, which in this case is 11.2 kilometers per hour, and direction is tan -1 of opposite which is opposite is VWE, VWE divided by adjacent, which is VBW. So if you plug those in a calculator, then you can get 26.6 degree. So velocity of boat relative to Earth is 11.2 kilometers per hour north, 26.6 east. Next one would be how far from home the motorboat will end up. So what we're looking for is this point here. So how far is the delta dx? You can calculate the delta dx using that big triangle. You see that big triangle? Delta dy, delta dx, and delta d total. So we know the angle now. We just calculated it to be 26.6. And we know adjacent. How can we find opposite? That's easy, because we know that tan of that angle is opposite over adjacent. So we have to solve for opposite. And opposite is adjacent times tan theta. And we know the opposite, we know the adjacent, which is 0.3 kilometer. And we can multiply that by tan 26.6 degree, and we get 0.15 kilometer. So 150 meter. If you point toward your home and there's a river is flowing, then that means that you are not going to end up here. You're going to end up exactly, and you can calculate exactly where you're going to end up based on a speed or based on the velocity of the water that is flowing. So it is exactly that you are going to end up somewhere precisely far from the home where you are aiming. Now, this is most important and most excited part of this problem, because now you are a captain. You have a boat. You know the river is flowing. You know that if you aim it straight up, you will not end up home. You're ending up 150 meters away from home. But you want to go home. So that's what you need to solve. How to get home. Where to aim the boat in order with a factor of water velocity can end up together directly home. That is a key. What would be this angle theta in order to take you home? Now, this is a vector addition of the two vectors. So it's a speed of the boat relative to water plus speed or velocity of the water relative to Earth will give you this result. So that's an equation. That's very important. However, for angle, you need to do something very simple. What is simple? Take a look at that angle here and the relationship of this angle with that triangle. In front of the angle is V, velocity of water relative to Earth. We know that. It's a 5 kilometers per hour. And this is hypotenuse, and we know that. It's a 10 kilometers per hour. So if we know hypotenuse and we know opposite, can we find angle? Yes, we can, because we know sine theta is equal opposite over hypotenuse, or velocity of water relative to Earth divided by velocity of boat relative to water. So now we can solve for theta, which is sin -1 sinus -1 of velocity of water relative to Earth divided by velocity of boat relative to water. So sine 5 divided by 10 is 0.5. Sine -1 of 0.5 is 30 degrees. We got it. Interesting thing is, if you would not go through this analyzing situation, if you don't go and use trigonometry to solve that problem, you may actually jump to the conclusion as we reached before, as angle between vertical and total BE, velocity of a boat relative to Earth, was 26.6 when you aim toward home. When you aim toward home, the water will take you somewhere here. So that angle here was 26.6. You may think that if I aim 26.6 here, that will take me exactly at the north direction. But it's not true. Why is not true? Because hypotenuse this time is 10 kilometers per hour, and opposite is 5 kilometers per hour. Before we had adjacent was 10 and opposite was 5. So it's totally different, and it's so easy to get confused. So now we know exactly what we need. We got that angle. We can go home. Now, how long will it take? How long will it take to go home? It is a constant motion because there's no acceleration on that one. So we can say, in order to, that 30 degree will help us to do this in two ways. Either you can use that adjacent of this angle when you have opposite, or when you have hypotenuse, or you can use Pythagorean theorem to find the side, which is the square root of hypotenuse square minus square of the side. So it is very straightforward. So 10 square minus 5 square is equal to 8.66 kilometers per hour. Or you can do, as I said, you can use sine or cosine if you want to use this for finding adjacent. Either way, you can do whatever you want. It's a many, more than one way to do that. However, that's the whole idea, is to find how long, the time. So time is crossing the 0.30 kilometer, crossing the river with a speed of 8.66 kilometers per hour north. That is distance north, speed is north, so that's one direction, so it's going to be, you ignore that north and north because they will cancel anyways. So the time now is 0.035 hours. That means 2.1 minutes. Do you remember that was 0.03 before to cross the river? So it is 2.1 minutes instead of 1.8 minutes that was. So it's going to take you longer. Yes, it's going to take you longer. However, it will take you home. That's the whole idea. That's how the pilots actually calculate the aiming, the angle that they have to go aiming toward somewhere in order to go exactly when they want. For example, if the airplane goes from New York to, let's say, Chicago, and there's a wind that is not on that direction, so a pilot has to take that wind speed and direction of that speed, direction of the velocity, in order to end up to the airport. Otherwise, it will go somewhere else, and that's not a good pilot. That's why relative velocity is important. Okay, this is a last practice problem for this relative velocity. This is more complex one, so I want you to get a piece of paper and calculator and a pencil and do it. Try it with me. The air velocity of a plane, we label it as a VPA, is 235 kilometers per hour, west 35 degrees south when the wind is blowing at 55 kilometers per hour, north 45 west, we label it VAG. Determine the velocity of plane relative to ground, we label it as VPG, plane relative to ground. Okay, so we know it's a relative velocity, and velocity of plane relative to ground is equal to velocity of plane relative to air plus velocity of air relative to ground. Since that none of those are on x and y, we draw those and we can, so VPA, it is with the 35, so west 35 south, and VAG with north 45 west, or it's the same thing as a west 45 north in this case. Okay, so next step would be, since that those are not on x, not on a y axis, you can draw component x and y, label it, and calculate it. For x component is adjacent, so that's why you use cosine. For y component is opposite, is in front of angle, that's why you use sine. And we have both negative. That's very important. Don't forget signs, because that's very important, because x is negative and y is negative. Now we do the same thing for VAG. We draw two components, we label it, and we can calculate it. For this is easier because sine 45 is equal to cosine 45, so both components are pretty much the same. So that's why we have negative 38.9, which is the x1. You see that direction is negative, and positive 38.9 because that is direction is up, is positive. So once you have those four components, you can add x component together and y components together. So x components, since they are both negative, you expect to be a big number, but negative. And since that we have bigger number, magnitude negative, and smaller positive, then the sum is going to be smaller in magnitude, but still negative. So those are values. Once we have those values, then we can draw those. So both negative, and we can use third quadrant, which x and y are both negative. Then we can draw x, and we can draw y, pretty much proportional, but you don't have to. Then you can draw hypotenuse, or velocity of the plane relative to ground. That's what we are looking for. Now, we have two sides. We can calculate angle, and we can calculate the hypotenuse. So using a Pythagorean theorem, you can calculate magnitude of velocity of plane relative to ground, which is square root of 231.4 square plus 95.9 square. The negatives doesn't matter because it's squared anyways. So the answer would be 250 kilometers per hour. We are ready to calculate angle, which we do opposite over adjacent. So tan negative 1 of opposite over adjacent. So the opposite clearly is y, and adjacent is x component. So tan negative 1 of 95.9 divided by 231.4 will give you 22.5 degree. So that angle is west 22 toward south. So west 22 degree south. Then the last thing is just write it down. Write it down as a velocity of plane relative to ground is 250 kilometers per hour, west 22.5 degree south. And that's it for today. I hope you enjoy it. I hope you learned something about it. Have a good day. Until next time. Goodbye.